So in this video, we are going to dig a little bit deeper into the equilibrium constant itself. In the previous video, I showed the equilibrium constant being written like this, and then after a while, I started drawing it as just being the letter K. But the thing is, there's actually a couple of different ways that we can write out K. For example, let's start off by looking at a particular reaction. Okay, so let's say that we have N2O4, which is a gas reacting in equilibrium to produce 2 moles of NO2, okay, which is also a gas. Now, based upon what we saw in the last video about how we how we write out the equilibrium expressions, K would be equal to the concentration of NO2 squared divided by the concentration of N2O4. And of course, these will be equilibrium concentrations, so after we've let the reaction go for a little while and reach equilibrium. Okay, but the thing here that's tricky is, well, the units that we're going to be using. Concentration is moles per liter. If we're going to express the value for K in this manner, we usually put a subscripted C to indicate that this K is being calculated on the basis of molarity. But it's also possible, and much more convenient in some cases, to express the to express the equilibrium constant in terms of pressures. Okay, so in this case, the partial pressure of NO2 squared divided by the partial pressure of N2O4. Okay, and this is just as viable. Pressure is really analogous to concentration when you think about it. And then when we're expressing the equilibrium constant in terms of pressure, we put a P there, and we call that the Kp. Okay, so these are going to actually be two different values, two different numbers for the equilibrium constant, based upon whether or not it's being reported in terms of calculations done with molarity or calculations done with partial pressures. Okay, so what we can do here actually is relate Kc to Kp, which is kind of a convenient tool that allows us to take the equilibrium constant from one way of calculating it to another. And here's how this works. Okay, we know that pressure times volume equals the number of moles times the gas constant times temperature. Now, if we divide both sides by volume, we get pressure equals the number of moles times RT divided by volume. And we can actually express this a little bit differently. We can take pressure and have it be equal to the number of moles divided by volume. So basically pull moles and volume out of that fraction and multiply that by RT. And when you think about it, the number of moles divided by the volume, which is in liters, is going to be the molarity. Okay, multiplied by the gas constant and temperature. Okay, so let's look at this in more general terms. Okay, so let's say that we are looking at some gas A being in equilibrium with some gas B. Okay, now we know that Kc is going to be equal to the concentration of B at equilibrium raised to the power of B divided by the concentration of A at equilibrium raised to the power of A. Okay, and we know that, oops, wrong character there, Kp is going to be equal to the partial pressure of B raised to the power of B divided by the partial pressure of A raised to the power of A. Okay, now we know the partial pressure of B is going to be equal to the number of moles of B times the gas constant times the temperature divided by volume. Okay, and the partial pressure for A is going to be equal to the number of moles of A times the gas constant times temperature divided by the volume. Okay, so what we wind up with here, if we substitute these values in, is that Kp is going to be equal to the number of moles of B times RT over volume over, and the whole thing up top raised to the power of B. Okay, so basically we just took that first expression and plugged it in up here. Now we can do the same thing for the second expression. Okay, all that raised to the power of A. Okay, now we can break this out a little bit, and we get the number of moles of B divided by the volume raised to the power of B divided by the number of moles of A divided by V is raised to the power of A times RT, and that whole thing raised to the power of B minus A if we're using our exponent rules. Now when you think about it, the number of moles of B divided by the volume is really just the concentration of B, and the number of moles of A divided by the volume is just the concentration of A. So what we wind up with here is the Kp being equal to the concentration of B raised to the power of B divided by the concentration of A raised to the power of A times RT raised to the power of B minus A. Okay, and if we sneak a peek back up here when we talked about Kc, okay, we see that this is the expression that describes Kc, which looks a whole lot like this right here. So this allows us to take Kp and set it equal to Kc times RT raised to the power of B minus A. Okay, where B is equal to the number of moles of gas in the products, and A is equal to the total number of moles of gas in the reactants. Okay, so this is kind of a handy equation here that allows us to relate Kp to Kc. Also, it kind of gives us another interesting insight here. If the number of moles of the gas in the product is equal to the number of moles of gas in the reactants, okay, so if A equals B, that means that Kp equals Kc times RT raised to the power of 0, which is going to be 1, so Kp equals Kc when we don't have an increase or decrease in the number of moles of gas. Okay, another interesting relationship. Okay, but notice that in order for this equation to work, everything had to be in the gas phase. And that's actually a very special set of conditions. We can have what's called a homogeneous equilibrium. And in a homogeneous equilibrium, all components are in the same phase. Okay, so for example, if we have hydrogen reacting with oxygen to produce water vapor, okay, everything here is in the gas phase. So this is a homogeneous equilibrium, if in fact it were at equilibrium. Okay, another example would be if we had aqueous HCl reacting with aqueous sodium hydroxide. So both of them dissolved in water, producing water plus NaCl. Okay. Now that is almost true.